Hello and welcome to the revision session for Physical Sciences grade 11/12. It's used for both grades, so we'll be discussing matters that has to do with Newton's laws of motion. But before we talk about Newton's laws of motion, we need to discuss the issue of forces, mainly how to calculate the magnitude of the kinetic frictional force given the coefficient of kinetic frictional force and relevant information to calculate the normal force or to determine the normal force acting on an object, which is of course will be on the surface. So dig deep into ways to go about simplifying for either the kinetic frictional force or static frictional force, and as well as the normal force. So we'll start off by looking at the most common equation which we use when we are calculating the kinetic frictional force or the maximum static frictional force, which is of course equal to the coefficient of kinetic frictional force or static frictional force multiplied by the normal force acting on an object. And now, the main issue usually is with the calculation of the normal force. We know the coefficient of static frictional force or kinetic frictional force describe the roughness of the surface, but then normal force takes different forms based on how the object is actually arranged on the plane. It's either it's on an inclined plane or a horizontal plane. So the calculation obviously will vary based on that information. Now, moving on from there, we see that normal force sometimes is equal to Fg, which is the most simplest situation that we can come across, or let me just say mg to be more specific and direct, right? So usually this happens when, and of course we know mg is equal to Fg. This one usually happens when the object is on a horizontal surface and there is no force acting at an angle. There's only an applied force or a tension causing an object to move horizontally on a plane. So if the object is moving horizontally, there is no vertical displacement of the object, meaning to say there's no vertical acceleration. Hence, we find normal force being equal to mg, because normal force will be acting vertically upwards, and then force of gravity obviously will be acting vertically downwards. So the sum of the two forces must be equal to 0, which is what we refer to as the vector sum of the two forces must give us 0. So that's the simplest scenario that you can ever come across, which will help you determine the magnitude of the normal force, and then you substitute it in the original equation, and then you simplify the rest. And then we move on to a bit more complex, but not that much complex. When we find normal force being equal to mg, which is of course Fg minus F sine theta, right, which you will see from the diagram, F sine theta being equal to the vertical component of the applied force. Now we have the force acting in 2D. It might be applied force, it might be the tension, it all varies. Now it is acting at an angle theta, so it's with thin the x and y axis, so to speak. So now the force, which might be the applied force or tension force or any force for that matter, which is relevant to your syllabus, will now be acting at an angle. So we are going to have a vertical component of this force going upwards, which is the one equal to F sine theta. And then we're also going to have the horizontal component, which we are not going to talk about for now. We'll focus on the vertical component. Now, this vertical component, which is opposite, of course, the angle theta, and the sum, the vector sum again, of all the forces acting horizontally, which is the normal force going upwards. We have the vertical component of the applied force also going upwards, and the force of gravity going downwards. When those two are added, then they add up to 0. So that's why we find normal force being equal to mg minus f sine theta. And then we're also going to have normal force being equal to mg plus f sine theta. Now, what's different from the one above? Now, the one above, we are pulling. And then in this situation, there is going to be a push. Now the vertical component of the applied force is no longer going to face upwards. It is going to be in the same direction as the force of gravity, meaning to say it is going to be facing downwards. So as a result, again, the vector sum of these forces is going to add up to 0 as well. Meaning to say, in that regard, normal force will be equal to the sum of mg plus f sine theta. Right, so that's why you find they say it is better to pull than to push, because the greater the magnitude of the normal force, the greater the resistance, which is the frictional force acting on the surface of the object. Now, this is just, one of those simple situations that you can come across when the force is. Now, let's consider an object which is placed on a inclined plane. Now, which is situation number 4. So in that situation, you'll find that normal force will be equal to mg cos theta, being mg cos theta being the vertical component, or should we say the perpendicular component to the plane of weight, which is our gravitational force. So there is an object on an inclined plane. There's angle theta, and we, in that regard, maybe we have a force being applied parallel to the plane, or there's no force. The object will be sliding downwards due to the parallel component of the gravitational force. Now, I think from the onset, when you do it in class, she's explained how or why do we use that angle theta, which is on the horizontal plane, as the angle in reference to the perpendicular component of the gravitational force. So I'm not going to delve much into that. I'm just going to talk about the application and the use of the formula in this regard. So we might have the applied force, or might have or tension, or any force for that matter, and obviously we're going to have Fg perpendicular, which is the perpendicular component of weight, and then we also have Fg parallel, which is going to maybe cause an object to slide downwards if, for some reason maybe the applied force is not enough to cause the object to go upwards, or there's no applied force at all for that matter. And then of course, perpendicular to the component, there are two forces acting, which is the normal force as well as the perpendicular component of gravitational force. So the vector sum of those two forces will obviously be equal to 0. And again, Fg perpendicular is the one which is equal to mg cos theta. So remember again, the angle that we use, the one that we see, which is theta there provided, will be equal to the angle in reference to the parallel plane. And then finally, the most rare one, which is number 5, that's when we find normal force being equal to the perpendicular component of weight, which is mg cos theta, minus the perpendicular component of the force, which might be the applied force. So allow me now to call the angle alpha for the perpendicular component of applied force or tension. Excuse me. So where do we find these situations? Again, we have our object on an inclined plane. Now we are going to have the force acting on an object. Now it is acting at an angle on an inclined plane. So the angle is the one that we are calling alpha in this regard. So force, it might be the applied force, tension, etc. Right. So the reason why I used alpha is to differentiate between these two angles. The one that we already know, which is cos theta, and the one referred to as alpha. So now, therefore, we have the perpendicular component of the applied force, or any force for that matter. That's the one that we are referring to. And then we're also going to have the parallel component of the same force. So our focus is on the perpendicular component at the moment. So this is one of those rare situations or scenarios that you come across, but you must be in a position to deal with them and respond to questions that would demand their application. So in that regard, normal force will be equal to mg cos theta minus the perpendicular component of the force which is acting on the object at an angle which is alpha in this regard. So let's consider the application by looking at one of the documents from Free State, which is the revision document 2021. We are going to start off by looking at question number 7. Now we can clearly see there is a diagram of two blocks, the 3 kg block and the 1.5 kg block. But then let's start off by reading the statement. It reads, the learner construct a push toy using two blocks with masses 1.5 kg and 3 kg respectively. The blocks are connected by a massless inextensible cord. The learner then apply a force of 25 newtons, as we can clearly see from the diagram as well, at an angle of 30 degrees, which is information that we need to take note of, to the 1.5 kg block by means of a light rigid rod, right, as you can clearly see there, causing the toy to move across a flat rough horizontal. Then if it is rough, then you know there is friction in that situation. Horizontal surface as shown in the diagram. So we can see there is a push being applied to the system on the 1.5 kg block using that rod. And then we also know again the surface is rough. Now we also are told that the coefficient of kinetic frictional force between the surface and each block is 0.15, which therefore tells us that the roughness of the surface is the same. or the blocks are made up of the same material. And then, of course, the first question will be state Newton's second law of motion in words, which I'm going to skip at the moment because you just need to know it from the top of your head what it simply means. And then 7.2 is now asking you to calculate the magnitude of the kinetic frictional force acting on the 3 kg block. The magnitude of the kinetic frictional force acting on the 3 kg block. So now when you look at the 3 kg block, you should think of the first thing that we spoke about, the first situation, because there is no force acting at an angle, or the force is acting on the 3 kg block. It's either they are parallel to the plane or they are perpendicular to the plane. So then for us to calculate kinetic frictional force, we already given the coefficient of kinetic frictional force. So what we need to determine first will obviously be the normal force, because that's the only missing information that will help us calculate the magnitude of the kinetic frictional force. So that will be the first step, calculating the normal force. We have the necessary information, which is the mass of the object, and obviously we know from the first scenario that or from the first situation that we had discussed already, that the normal force is actually equal to the mass times acceleration due to gravity of the object. So we'll be applying that. That's when we determine the magnitude of the normal force. Then we can go back and calculate the magnitude of the kinetic frictional force. So response, the first thing that you do on 7.2 will be calculating the normal force, which is equal to mass times acceleration due to gravity. The mass of the object is 3, acceleration due to gravity is 9.8, which is a constant. And then when you simplify that, you find your answer to be 29.4 newtons. And then you go back to your original equation for calculating kinetic frictional force, and you do the substitution now. Your coefficient of kinetic frictional force is 0.15 as provided, and then multiplied by the magnitude of the normal force, which is 29.4. And then you'll find the answer to be 4.41 newtons. So it's as easy as it looks. We have now determined the magnitude of the normal force as requested or is required by the question. And then of course we move on to the next question, which is 7.3, which is now asking us to draw a labeled free body diagram showing all the forces acting on the 1.5 kg block. So whenever we talk about the free body diagram, it simply means then we are applying the dot to our free body diagram. But I think for this one, I'll need to open a blank page so that the drawing will be clear for 7.3, and then from the drawing we move on to problem solving, which is for 7.4.1. Feel free to pause the video and draw your free body diagram. Okay, now let's get started. So a free body diagram will be represented by a dot. I'm going to make it a bit larger because I'll be using components instead at some point. So obviously because the object is on a surface, so I'm going to draw a faint line to represent the surface. And as a result, the object being on the surface, it is going to experience normal force, which is going to be perpendicular to the surface, and it is going to be a bit longer. And then because it's an object of mass, there's going to be force of gravity, which is Fg, going downwards, which is a bit shorter. And then of course we are told that the object is on a rough surface. There's going to be kinetic frictional force, and there is a cord connecting the 3 kg block and the 1.5 kg block. So we're going to have tension, and then finally there is a push force, which is going to give us the applied force, which is obviously going to be in 2D in that regard, going downwards. I much prefer the free body diagram drawings to be that of components, because it is going to assist you as a learner when you are dealing with calculations. So we're also going to draw a free body diagram using components, which is the one that I much prefer, because it makes your life easy and identifying which force is acting where, right? So next to the one that includes forces, we are going to look at the one that is going to have the applied force in form of components, which is we're going to have a vertical component and a horizontal component. So there we go at the bottom. We are going to have the object on the surface as normal, and then the rest of the forces are going to be there as normal. We're going to have the normal force going upwards. We're going to have the force of gravity going downwards, and then we're also going to have tension and kinetic frictional force to the left, and then finally we are going to have the vertical component of the applied force going downwards, and then the horizontal component of the applied force going to the left, right? So we're going to have Fy and Fx, and we know Fx is F cos theta, and then Fy is F sine theta, which is going to make it easy for us when we are dealing with any problem solving. So that will be it, the solution, or what is expected from you for 7.3. So remember, again, not something. Components are represented by dashed lines because they are not the actual forces. So there must be a difference between the component of a force and the actual force. Now let's consider 7.4.1, which says we should calculate the kinetic frictional force acting on the 1.5 kg block. Now, if you look at the 1.5 kg block, there is a pushing force of 25 newtons at an angle of 30 degrees to the horizontal. So let's consider the diagrams that we had before, or the situations, and see which one is applicable. I think that will be, according to this one, will be number 3, which we can clearly see that there is a push being applied. So obviously the first thing that we need to know is to calculate the normal force. So the normal force will be calculated using mg plus f sine theta, because we can clearly see that there is a push at an angle of theta. So therefore the equation applicable to the situation that we are dealing with right now is number 3. So let's see how this is gonna work for us and how we are going to determine everything. So 7.4.1, let me use a different color, which is the white one. I think will do better. 7.4.1, the first thing that we need to do is to calculate the normal force, of course, using mg plus f sine theta. So if you recall very well, you'd know that the magnitude, or let's just go and check the information so that we are going to be all on the same page. So the mass is 1.5 kgs, and the one that we are dealing with right now at the moment, and then the applied force, or the force being exerted, is 25 newtons at an angle of 30 degrees. Hopefully this information will be easily remembered, as we'll be dealing with problem solving on the other page. So going back again, so the mass is going to be 1.5 multiplied by 9.8, which is acceleration due to gravity, plus the force, which is 25 newtons, 25 newtons, yes, and then sine the angle is 30 degrees. So if you punch that into your calculator, the numerical value should be 27.2 newtons. Right, but then we are not done. That's not what we are supposed to, or what we are asked to calculate. We are asked to calculate the kinetic frictional force. So again, kinetic frictional force is the coefficient of kinetic frictional force multiplied by the normal force, and then the magnitude of the kinetic frictional force, as remembered, is still 0.15, sorry, multiplied by the normal force that you just calculated above, which is 27.2. And then if you again punch that into your calculator, the answer must be equal to 4.08 newtons. So that's the magnitude of the kinetic frictional force acting on the 1.5 kg block, which I think is simple and straightforward. Having applied the first and the third scenario in the ones that we discussed, and then so we'll go back again and see what the next question is about. So the next question, 7.4.2, is asking us to calculate the tension in the cord connecting the two blocks. So usually when we have the two blocks being connected by a string, then to some degree we need to solve for that problem using the simultaneous equation. And so that's when we'll consider the horizontal forces now, not the vertical forces that we've been talking about. So we have to consider the horizontal force acting on the 3 kg block, as well as the horizontal forces acting on the 1.5 kg block. Likewise, so that's when you find the importance of drawing a free body diagram using components, because now it makes it easy for us to deal with the situation on the 1.5 kg block. So again, we go back on a working space and see if we can solve for 7.4.2. So we're going to start off with the 3 kg block. Let me first write the number 7.4.2. So 3 kg block, that's the first one that we'll start with, because there is tension on the 3 kg block. Now, again, the starting point, we are now horizontal. F net is equal to mass times acceleration of the system, and then now we consider the vector sum of all the forces acting on the 3 kg block horizontal the plane, which is, we have the tension going to the right, so we are taking to the right as positive in this problem solving. And then since we have tension going to the right, we're also going to have the kinetic frictional force, which is in the opposite direction as the direction of the system. That will of course be equal to mass times acceleration due to gravity, acceleration, sorry. So tension, that's what we are supposed to determine, minus the magnitude of the kinetic frictional force from 7.2, if I'm not mistaken, was equal to 4.41, if you can recall very well from the previous problems that we looked at. And that will of course be equal to mass, which is 3, acceleration is also unknown, and then we make t the subject of the formula in this regard. So when we do that, then we'll find that tension will be equal to the mass, which is 3, times acceleration, supposed to be plus right there, and then that will give us equation number 1, and I'll sort it later. Now we then move on to the 1.5 kg block. Now the 1.5 kg block, again same story. F net is equal to ma. The mass of the block is 1.5, but then we of course have to consider the vector sum of the forces acting on the 1.5 kg block. So the one which is going to the right will obviously be fx, which is the horizontal component of the applied force, and then the rest are going to the left, so it's going to be plus or minus tension, and then finally we have plus or minus kinetic frictional force. That will of course be equal to ma. Now we move on and look at the substitution. So fx is f cos theta, so the magnitude of f, as we have already seen it previously. Let me just create space for the further calculation that I need to do here. So fx, from what we know, it is going to be f, which in this case is equal to 25, cos the angle is 30 degrees, minus tension, minus the kinetic frictional force for the 1.5 kg block as calculated in 4.1 is 4.08. And then of course that will be equal to the mass, which is the screen is giving me some problems. The mass, which is equal to 1.5 times the acceleration, which is a. And then moving forward, then we simplify and at the end make t the subject of the formula. So further to that, we are going to have simplifying just a moment, trying to find the calculator. So that will give us 17.57 minus tension is equal to 1.5a, and then further making t the subject of the formula. So we're going to have 17.57 minus 1.5, minus 1.5 actually not equal to, it's minus 1.5a. That will be equal to tension. So we know again then the tension on the 3 kg block, that gives us equation number 2, not 1. Equation number 2. And then from that we draw the conclusion. We know the tension on the 3 kg block is equal to the tension on the 1.5 kg block, sorry. So Therefore, from that, we can then conclude that 3a minus or plus supposed to be positive. We just have to correct that when I'm done writing the expression for the 3 kg block. So it's 3a plus 4 point, I'm repeating the same mistake of minus here. I'll fix it at the end. So I have to simply calculate or solve for the acceleration first before I solve for the tension. So it's 3a plus 4.41, which is equal to 17.57 minus 1.5a. And then 3a plus 1.5a, that's 4.5a, being equal to 17.57 minus 4.41. The calculator gives me 13.16. And then to divide both sides by 4.5 and determine the acceleration of the object. And then from the acceleration of the object, which is 2 point something, we move on and then we substitute that same information in either equation 1 or equation 2 of our tension and see if we can determine the magnitude of the tension. So both equations must give us the same magnitude. If not the same, then there must be close values. So what might be the result of us getting a different answer, slightly different answers, because we have been rounding off when calculating for anything that we have calculated above. So then taking equation 1, we see that tension is equal to 3, which is the mass, times the acceleration, which is 2.92 plus 4.41, and which is our current frictional force. If we simplify this further, you'd find that the magnitude of the tension connecting the 3 kg block and the 1.5 kg block from your calculator is 13.18 newtons. So this is now applying Newton's second law of motion, which we didn't discuss in depth, but then we had to look at this question in as much as we said we need to talk about those situations when we need to calculate the normal force, but then it was part of the questions that we needed response. So then one had to consider that one. So yeah, that's what was expected from us as learners. So let's see if we can look at another question as well, which is in this regard. We're going to look at question 8. Question 8 just below question 7, which reads, a crate of mass 2 kg is being pulled to the right across a rough horizontal surface by constant force F. The force is being applied at an angle of 20 degrees to the horizontal as shown in the diagram below, or next to the statement, sorry. So now draw a labeled free body diagram showing all the forces acting on the crate. Again, now what's different in this case? There is an applied force which is being applied at an angle of 20 degrees to the horizontal, which is of course is a pulling force. So one must be in a position again to know whether I can use components or I just have to use the forces which are there. So much preferably so, components will make it easy for you, Okay, then let's proceed. Free body diagram, dot is representing the object, and then the green line representing the surface. And then, of course, we have the normal force going upwards, and then we have Fg going downwards. In this regard, Fg is going to be longer than the normal force, because normal force in this regard will be equal to Fg minus the vertical component of the applied force. Now, because we are also told that the surface is rough, so obviously the free body diagram must include the friction which is acting on the surface of the object, because we are told that the surface is indeed rough. So there is kinetic frictional force, and then of course there is that applied force at an angle of 20 degrees. But then of course, much preferably, the components will do it better, because they will make it easy for you to deal with problem solving. So again, the dot is a bit larger, because that will there's involvement of components. There's going to be the green one for the surface, and then of course we have the normal force, the kinetic frictional force, and gravitational force, as we had in the first one. And then we now have the vertical component of the applied force, since the object is being put at an angle, which is Fy, and then we have the horizontal component of the applied force, which is of course in this case going to be equal to Fx. So this what would be expected from you as a learner. It's either A or B, but I much prefer the second one, because it will also help you when you're dealing with problem solving. And then just below the drawing, there is a constant frictional force of 3 newtons acts between the surface of the crate, and the coefficient of kinetic frictional force between the crate and the surface is 0.2. Calculate the magnitude of the normal force acting on the crate. So this one, I think, it's simple and straightforward. We are told that we have the magnitude of the kinetic frictional force, and then we also have the coefficient of kinetic frictional force. So from the formula, Fk is equal to mean K times normal force. I think it becomes very easy to determine the magnitude of the normal force in that regard, because we have the coefficient of kinetic frictional force, it is given to us, as well as the magnitude of the frictional force. So it makes the response for 8.1.2 very easy and direct, because we have the necessary information to deal with that. So yeah, let's see if we can find the solution to the problem by doing the necessary substitution to the formula. So obviously you have to divide both sides by 0.3, and then when you do that, the magnitude of the normal force will be equal to 15 newtons. Hopefully we both got the same answer. Now, moving forward, 8.1.3 now says we have to calculate the magnitude of F, or force F, in other words. Now we have to consider two things, whether we're using the horizontal components or the vertical components of the plane. Now, going back to what we once looked at, then you know it is going to be easy for us now to consider the vertical components, because there's much information that we have. We have already calculated the normal force, And we also have or we can easily calculate the magnitude of the gravitational force acting on the system. Now, as we have already seen from the diagram, this is situation number 3, which talks to an object experiencing a pulling force. Then, in that regard, we know that normal force then will be equal to mass times acceleration due to gravity, which is Fg, minus the vertical component of the applied force, which is in this case is F sine theta. Right. So now, substituting back the information, then we've already calculated the normal force from 8.1.2, which is 15 newtons, and then the mass of the object is 2. Acceleration due to gravity is also a constant of 9.8. The screen keeps moving each time I try to do the writing, but hopefully you'll get this one sorted out. Yes. Now, I'm forgetting now to include the 9.8. I'll include it just now. So this is minus F sine theta. So the magnitude of F is what we are looking for in this instance. So we know 2 times 9.8, that's 19.6. And we just have to do the math the way it's supposed to be done. By transposing then F, we're going to have F sine 20 being equal to 19.6 minus 15. And then from there, you'd see 19.6 minus 15 will give you 4.6. And then we have to divide both sides by sine 20 degrees so that we can have the magnitude of F is required by the question. So in that regard, you'd find your answer to be, let me just punch this into the calculator. Yes, the answer that I'm getting is equal to, just one moment, this calculator is not coming right. Okay, it is equal to 13.45 newtons. So that's the magnitude of the applied force, which is being applied at an angle of 20 degrees. So yeah, I think that will be it. The solution for 8.1.3. And then obviously the last question we'll talk to, just have to look at what